2, right? X and y. So of course you need two equations. So this is one equation. What's going to be the second equation?
Wait, why did you call f of x?
Sorry?
Why did you call f of x dy? Why is there two negatives?
Because slope is minus, so this, I can write this as minus gx. Subscript means derivative. Right?
Right?
And similarly I can do the same thing with f.
But why are there two negatives?
Because slope has a negative in there, as I show here.
Yeah, we have two.
Right?
Oh. Okay, that's what you're saying.
Okay? Alright, good. So that's of course our one equation. What's going to be the second equation?
The sum of those two equations.
Sorry?
Maybe the sum of those two equations?
The functions are the same there? Are the functions also the same?
You could actually, that's not the case. F is not equal to g, right? Because f is a constant. But you are close. What is the other equation? We are marching where? Our constraint is g equals to 0. So that's the second equation, right? The constraint. The second equation is g equals to 0. Right? Yeah? Okay, I think hopefully this will become clearer in a minute when we do another example. So let's now do another example where f, let's say, still is xy, but a constraint g is x squared plus y squared minus 1 equals to 0. Okay? So what does this constraint represent? A circle, right? Very good. So our constraint now is a circle. Right? And this f equals to constant. So let's plot f equals to 1. What does xy equal to 1 curve look like? Straight line? xy equals to 1 is a straight line in xy plane? Sorry? Like this, right? In fact, actually, you know what? Let me plot first equal to 0. That will clarify why. So what is xy equals to 0? What curve is that? Y axis. Very good. Those are two axes. Those curves simply are this, this. And we can see xy equals to constant will basically be curves that will look like this. Right? But what's happening to the product? As you are saying, now you can see that those are the f equals to constant curves, and this is the constraint. Now, of course, there will be a 4 family of curves, right? There will be 4 family, one in each quadrant. Just for a second, let's just look only at the positive part. Okay? All right, so now we can, so now, just for fun, let's just now write down the value of f on some curves. So here the value, of course, is 0, right? Let's look at the curve where actually it's just tangent. So it's tangent. You know it will be tangent where essentially at the midpoint, right? So from symmetry, you already know what it would be, right? So the x equals to y, so it will be y squared equals to 1. So 1 over square root of 2, 1 over square root of 2, right? Does it make sense? So you know this point already. So you know that this curve will be xy. This will be f equals to r. And then you can have, so don't worry about it. Imagine, pretend I'm just plotting it because of whatever, f equals to 1, f equals to 2. So you can see I've plotted this curve, and this will, let's say, f equals to 1/4. So you can see now, imagine you're walking on this. You see 1/4, you keep walking, you see 1/2, then finally you start seeing lower values again. So you can see this has to be the bottom axis. Right? So graphically does it make sense? We'll do it mathematically, but I just want to make sure graphically it makes sense to everybody. Yeah? Okay, so now let's do it. So let's calculate. So these are the two equations we have to solve. So let's look at this equation: fx over fy equals to gx over gy. So, so fx. Well, actually, we can just do it right here. Fx. You already know f equals to xy. So what is fx? Fx is just y, right? And what is fy? Yeah.
So it doesn't actually matter what constant we set f equal to, it's just the fact that at a particular constant.
Right, exactly. So you are plotting a bunch of different constants. Ahead of time, you don't know which one will be tangent. I just kind of knew it because it's a very simple problem. So think of various different isobars, right? These are called isobars because the values are constant, right? So, so yeah, essentially at some value of that constant, which is actually unknown right now, these two curves will be tangent. We don't know that value, that's why we're solving the problem, right? We want to find out that value, but conceptually at certain values they will be tangent. I just wrote half because it's an easy problem. I know the solution in my head, so I can do it. But yeah, in big thing you will not know where it is tangent. You will start randomly constructing curves, some of them will be here, some of them will be here, right? Okay. So fx is y, what is fy? X, very good, equals to gx. What is gx? Sorry? 2x, very good. And what is gy? 1. Very good. So you can see basically you get x squared equals to y squared. Right? So that's one equation. And what's the second equation?
G is equal to 0.
G is equal to 0, which means x squared plus y squared equals to 1. All right, so all we do is we substitute this x squared equals to y squared into this equation, and essentially solve for x and y. So therefore you substitute this, therefore you get 2y squared equals to 1, and therefore y is plus minus square root of 1 half. Right? Now, of course, you also want to figure out what x is. So you plug this y back into this equation to figure out x. And therefore, you get x squared equals to 1 minus y squared equals to 1 minus a half. Right? Therefore, x equals to also plus minus 1 over square root of 2. And therefore, you can see here 4 solutions, right? And the 4 solutions are obviously this, 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 and this.
How would that actually top left quadrant and bottom quadrant satisfy?
How did what?
Those aren't maximums, those are minimums.
Very good. Now you can interestingly, if you think about it, if you're walking in a circle, what can you say about maximum and minimum? No, I mean between any two maxima there has to be a minima. So yeah, two of these are maxima. It's like saying maximum maxima. What does it mean maximum minimum? It means there has to be a minimum. Otherwise it's a straight curve, which by definition these two are not maximas. Right? So yeah, two of these are maximas and two of these are minimums. So the maxima of course is f product, so basically half and half. So this is f equals to half, f equals to half. This is f equals to minus half, minus half. Right? Make sense? And like I said, you can actually now, if you think about it, you can now draw a curve of f as a function of s, where s is the arc length. Right? So arc length basically will go from 0 to what? Sorry? 2 pi. Very good. And now you can start plotting the value of f. And you can see that there will of course be arc. Well, it also depends on where you start. Right? Let's say you start arc length here. So there, you know the value is going to be 0. So basically, if you go from 0, this, that's the minimum. I'm not drawing a sine curve. I don't, obviously, basically the shape will look like this. So there are 2 maximas and 2 minimums. Right?
Since you started at 0, in that circle, isn't it essentially a sine curve?
No, it's not going to be a sine curve, right? Because f is x squared plus y squared. It's not going to be a sine curve. I mean, f is xy. F is xy, so there's no sine or cosine or anything like that. Actually, I mean, you can see. So f, what would be f? xy equals to x times y. So y is going to be x. Right. But the idea is you're plotting it as a function is a point of arc length. So you have to convert arc length to x. So x in terms of arc length, you know what it is, right? So s, yeah, you have to convert to angle representation and things like that. So anyway, but does everybody get the idea of constraint optimization? Okay, so constraint now, as you can imagine, constraint optimization is very, very common in chemical engineering, or any engineering for that matter. Because frequently you have constraints, like your conversion maybe has to be fixed, right? Or maybe your pressure drop is fixed because you have a pump that cannot go above certain pressure. So any kind of unit operation you can think of, you can very easily imagine certain constraints, right? So you have to optimize in the face of those constraints. And so yeah, like I said, constraint optimization